Hello, my name is Etienne Jumel and I will be presenting you in this short video the basis of nuclear fission and nuclear energy. Nuclear energy is relatively new in the history of mankind. It was based on a scientific breakthrough in 1938 and was back then exclusively reserved for military purposes before even producing electricity. Nowadays, nuclear energy is not understood by a large number of people. This video has the purpose to explain how nuclear energy works. We believe that citizens everywhere need to first understand nuclear energy so they can then properly judge whether it is a threat or a valuable source of energy, or maybe somewhere in behind. What is everything really made of? Questions like this have been asked for centuries, and scientists are still trying to find the correct answer. At one time, scientists believed that the smallest building block of matter was the atom, a name that comes from the Greek word meaning incapable of being divided. Later, it was discovered that an atom was made up of smaller particles. However, the atom is still the smaller part of a single body able to chemically react with another. So far, 92 naturally occurring elements have been discovered. The elements are organized in a periodic table based on different properties, which we're going to detail. First, the dense central part of an atom, called the nucleus, is made up of protons and neutrons. Protons are small particles with a positive electrical charge. The number of protons in an atom is called the atomic number and determines the identity of the atom, what element it is. Neutrons, as their name implies, have no electrical charge, but they add significantly to the mass of an atom. In fact, the approximate atomic mass is the sum of the mass of the protons and the neutrons added together. The atomic mass is listed right under the element symbol on the periodic table. Though all atoms of a particular element will always have the same number of protons, sometimes the atoms of that element can have a different number of neutrons. These are called isotopes, and carbon is a good example of it. An atom also contains other particles called electrons, which orbit around the nucleus. These have so little mass that they are ignored when calculating the atomic mass. Electrons have a negative electrical charge that balances with a positive proton charge in the nucleus to form a neutral atom. Given enough energy, however, electrons can sometimes jump away from an atom, ruining the electrical balance and giving the atom a positive charge. Likewise, sometimes an atom can gain an extra electron, giving it a negative charge. Atoms with unbalanced electrical charges, either positive or negative, are called ions. Positive ions, atoms that have lost electrons, are slightly smaller than the original atom, while negative ions, which have gained electrons, are slightly larger. As most people learn in their science integration, opposite charges attract each other while equal charges repel each other. Therefore, if you consider that the nucleus of all atoms, except hydrogen, contain more than one proton, and each proton carries a positive charge, then why would the nuclei of these atoms stay together? The protons must feel a repulsive force from the other neighboring protons, right? Well, this is where the nuclear binding energy comes in. Nuclear binding energy is one of the 4 basic forces in nature and is the strongest among of them. However, it has also the shortest range, meaning that particles must be extremely close to each other before this force is felt. It is an attractive force that holds together the subatomic particles of the nucleus that we introduced earlier. But how can nuclear fission happen? In the previous part, we've pointed out that the complexity of the atom, and especially the existence of a nuclear binding energy, required to keep the protons and neutrons of a nucleus intact. We now have the basic tools to understand nuclear fission. Nuclear fission is the splitting of a heavy nucleus into two lighter ones. In nature, nuclear fission very rarely happens, spontaneously at least. But in nuclear power plants, it can be induced by free neutrons. As a result, two lighter atoms are produced as well as a couple, 2.5 on average, of free neutrons. When a large nucleus splits in two, i.e. undergoes fission, the combined mass of the resultant smaller nuclei and neutrons is less than the mass of the original nucleus. In both cases, there is said to be a mass defect between the reactive and the product. The missing mass is in fact released as energy, and the amount of energy released can be calculated using the mass-energy equivalence relation discovered by Einstein, E = mc². The total energy that is released when a nucleus is formed is called the binding energy of the nucleus. Conversely, the binding energy can be thought of as the energy that must be supplied to break up a nucleus into its individual constituent protons and neutrons. You can see on this curve, representing the average binding energy per nucleon as a function of the atomic mass, that the largest binding energy, which means the highest stability, occurs near mass number 56, the mass region of the element iron. It indicates that any nucleus heavier than mass number 56 is less stable. Not all heavy atoms fission spontaneously, because barriers to such spontaneous conversion are provided by other factors which form what is called the fission barrier. This fission barrier represents the amount of energy that we necessarily have to bring in order to break the nucleus apart. The majority of nuclei have a fission barrier impossible to break through, and the very few isotopes which can fission after absorption of a neutron are called fissionable and can be separated in two categories. The first shows fission that can be induced with slow, low energy neutrons, while the second set requires fast, high energy neutrons. The first category has a special name, namely fissile material. Most nuclei that are fissile contain an odd number of neutrons, like uranium-233 or 235, or plutonium-239, whereas most of fertile nuclides, thorium-232 or uranium-238, have an even number. The addition of a neutron in the former case liberates sufficient binding energy to induce fission. In the latter case, the binding energy is insufficient to surmount the fission barrier, and additional energy must then be supplied in the form of the kinetic energy of the incident neutron. A nuclear reactor is designed in such a way that each time a fission reaction happens, the released neutrons induce on average one other fission reaction. By maintaining such a chain, it is possible to heat water and produce steam, which makes turbines rotate and generate electricity. The nuclear wastes of a power plant are classed in different categories. First, the low-level waste is generated from hospital and industry, as well as in the nuclear fuel cycle. It comprises paper, rags, tools, clothing, filters which contain small amounts of mostly short radioactivity. It does not require shielding during handling and transport and is suitable for shallow land burial. To reduce its volume, it is often compacted or incinerated before disposal. It comprises some 90% of the volume, but only 1% of the radioactivity of full radioactive waste. Then the intermediate level waste, which contains higher amounts of radioactivity and may require some shielding. It typically comprises resins, chemical sludges, and metal fuel cladding, as well as contaminated materials from reactor decommissioning. Smaller items and any non-solids may be solidified in concrete or bitumen for disposal. It makes up 7% of the volume and 4% of the radioactivity of all radioactive waste. By definition, its radioactive decay doesn't generate enough heat to require heating to be taken into account in the design of storage or disposal facilities. Then comes the spent fuel. It's the fuel that results after being irradiated for a certain amount of time in a nuclear reactor. It is then reprocessed in two separated parts. First, in a fuel that can be reused, and second, in a high-level waste. The high-level waste arises from the fission of uranium in a nuclear reactor. It contains the fission products and transuranic elements generated in the reactor core. Transuranic elements have atomic number greater than 92, the atomic number of uranium. Those elements are created by neutron capture in uranium instead of the fission reaction. High-level wastes are highly hot due to decay heat, and its reactor activity requires cooling and shielding. They have high thermal load and can be considered as the ash of burning uranium. They account for over 95% of the total radioactivity produced in the process of electricity generation. This categorization, high, intermediate, low, helps to determine how wastes should be treated and where they should end up. While high-level wastes require big shielding and cooling, low-level waste can be handled easily without it. All radioactive waste facilities are designed with numerous layers of protection to make sure that people remain protected for as long as it takes for the radioactivity to reduce to background levels. Low-level and intermediate waste are buried near to the surface. The high-level waste remains highly radioactive for thousands of years and needs therefore to be disposed of in deep underground facilities built in stable geological formations. No such facilities for high-level waste is currently in operation, but the feasibility has been demonstrated, and there are several countries now in the process of designing and constructing them. Finally, the majority of used fuel is reprocessed to recover the valuable fissile material, which will be then recycled into new fuel. Compared with other industrial waste generated, the volume of nuclear waste produced by the nuclear industry is very small. A typical 1000 megawatt electrical light water reactor will generate only 27 tons of used fuel per year and run 1 ton of fission products. This compares with an average of 400,000 tons of ash and many million tons of CO2 produced from a coal-fired plant of the same power capacity. The total volume of nuclear waste produced can be considered as being small in the shadow of the worldwide waste. Therefore, the most important issue and challenge for the nuclear industry is to manage the toxic waste in a way that doesn't harm the environment.